for Arizona, but I think we're very lucky we're not anywhere else in the country right now, honestly. Because I was freezing on my way here and thinking, no, it's not freezing. But, so a week from today is our first class exam. And I posted after class on Tuesday, not too long after class on Tuesday, an announcement, despite the fact that there's not a whole lot on here. You can still access the announcements that, I don't know if you have them set to be automatically sent to your email or not, but announcements are in Canvas, my version and your version. And the one that I sent on Tuesday has an attachment in it. I'm going to post this someplace in iMath, but it was being stubborn and wouldn't let me do it last time I tried. So in any case, it's in here. This exam review is just a whole ton of questions, assorted things. I'm going to post solutions to those over the weekend also, but I wanted you to take a look at them first. We're going to talk about a little bit of that today, but a week from today is your first test. It is multiple choice. It's going to be Scantron. Make sure you bring a pencil. But not nearly as long as that exam review. It's like 20 questions, but the way the exam review is set up, it's like 50 questions, but each question has 5 sub-questions. So the exam review is like 150 questions, seemingly. The actual test is 25, so it'll be considerably shorter, reasonable length, and because there are both Tuesday, Thursday, and Monday, Wednesday, Friday classes of this course, our exam period, we only have 50 minutes to do it, so it's not going to be the whole class. It's a 50-minute exam. So on Thursday next week, we'll start at 7:30, and we'll be done by 8:30 by the time we get everybody checked in and out. So in any case, what I want to do today, talk a little bit more about function composition and then also decomposition, like how to undo the process of composing functions or think about how they're put together, complex functions. And then a little bit about inverse functions. And then we'll talk about some test-related things, just examples. So let's see, where is it going to go first? Oh, so I did have posted on here, I just put this up like 20 minutes ago. There's a link here if you want to pull it up on your own device. It says examples used in class Thursday, February 3rd. That's today, so we haven't used them yet. But I'm going to pull them up in this format so I can type on it. But what this is, function composition and decomposition. And we talked about the idea of function composition with respect to what we're using, perimeter and area of a square. So we had a formula that we wrote that would take the perimeter of a square and turn it into side length, and then a formula that would take the side length and turn it into area. And you can do those in sequence, or you can kind of combine them and make a single formula out of it. But you've done some other online work in iMath with function composition also. And I'm sure most of you have seen it before in some previous class or another. But what I want to do is take some time and see what you can figure out on these, and then we'll go through them together in a little bit. But I want you to work on your own, work together. Utilize the fact that we're all here in the same place. Take a little bit of time. I'm going to see if I can zoom this in a little bit more. Here, I can just unofficially. There we go. So we want to write function rules for f of g of x and g of f of x. Don't simplify, just pop the functions together, so make them do in sequence. Remembering that the expression f parentheses g parentheses x, f of g of x, indicates that in terms of the sequence of events, if you're doing things order of operation wise, we do g of x first, and whatever the result of that is, we do function f to that result. We do f to the function g of x result. So f of g of x, there's kind of f of 7 means plug 7 into the f formula, if you want to think of it that way. F of g of x means I take the g of x result, the whole formula result, and pop it into the f formula in terms of generic function notation stuff. We're talking more applications of this last week, or last class. But I just want to talk about general, like, how does this work? What do we do in general? And without a whole story to go along with it, if we could just focus on the mechanics of this a little bit, the boring part. But I wanna make sure that you do have the boring part down so that you can do this when needed and don't get tangled up in the algebra of it. But again, don't worry about simplifying, just you can do these function compositions. I'm gonna scroll this up a little bit, so if you're ahead, you can see what we're gonna be doing with that table. There are several more examples of what's going on with that table also. The reason we would ever do this is because, like with the example, the output of one function is useful as the input to a second. So we have two related processes. And we have to do them in specific sequence. So normally, like swapping orders like that, in most applications, that doesn't make particular sense, one way or the other. But for algebraic purposes, we're going to see how this works if I do one way versus the other, in terms of which comes first. Anyone having internet connectivity issues this morning? Okay. But yeah, I know sometimes. Let's see if this will. Why are we doing this? All right, so take a look at this first question. We want f of g of x I mean, so imagine this was the same side length perimeter sort of situation we were dealing with earlier, where maybe in this case, first I do g of x, which takes a perimeter and turns into the side length. Not really, because it's this square root of 5x. But then that result, if this is our side length, I'd want to plug it into this other formula to get the area of our square. Now, these clearly aren't area and perimeter side length of square relationships here, but same premise. This g of x is what we're doing first in this, and I'm taking the result, square root of 5x, and putting that result, whatever it may be, and this is asking for f of g of x, not f of g of a specific number. So here's my g of x, and I can even think of it like that, like, oh, well, I want f of 5, the square root of 5x then, because g of x is equal to square root of 5x, so I can think of that, in which this symbol means I take f's formula and plug in square root of 5x for its variable. So that means in that spot. So if f of x is 3x minus 8, then instead of 3x minus 8, I'm going to have 3 times this square root of 5x in that spot. I'm just trying to do copy and paste to save some time here, but 3 times square root of 5x minus 8 instead of 3x minus 8. So if you can see, it's just, and this is why copy and paste works well with this. Don't simplify anything. Just, oh, I'm taking this expression and plugging it in a different spot. I don't have to take any square roots of something. It's the square root of 5x. Now, if this had said f of g of 5, then I'd say, oh, g of x is the square root of 25. So, oh, that's 5. And then I'd plug 5 in here and say 3 times 5 minus 8, 15 minus 8, 7. And I could get that result. I could also do that all at once here. 3 times that square root of 5x minus 8. And so if you do have to do a sequence of processes over and over and over again, or want a general formula for how this sequence of processes comes out, that's why you might want to write a composition of functions instead of keeping it as 2 separate processes, or more than 2. But this is f of g of x. If I wanted to go the other way around, yeah, question? So if I said find f of 19, I'd put in 19 right in that spot where the x is, right? So if I want f of square root of 5x, I'm going to put square root of 5x right in that spot. It's this same idea. I'm replacing whatever's inside the parentheses, just notation-wise. That means that's what my input is. Whether it's a number, or whether it's a formula result, or just the name of something else, even like g of x. We're just replacing that input variable in the function rule. In the formula it says, how do I calculate s? Yeah. So the other way around, yeah, for sure. The minus 8 is going to be underneath the square root sign, because if I want to do, let's see, let me copy and paste again. G of f of x. That means my overall structure of my function is like this, but instead of having a square root of 5x, I'm going to have function g evaluated at this. If you want to think, okay, so g of f of x means g of 3x minus 8, meaning I'm plugging 3x minus 8 into function g, or I'm taking the result, whatever the value of 3x minus 8 is from something, and taking a square root of 5 times that. So in this case, this, instead of having square root of 5x, which is g of x, I'm going to replace this x with 3x minus 8. So I'm just going to retype that. Oops. There we go. So instead of 5x, I have 5 f of x. underneath the square root. And so that -8 ends up underneath. All right, so just algebra-wise, combining the formulas together. When you have a meaning for the formula, it's almost easier, even though, like, probably initially in life, story problems, like, oh my gosh, story problems are so hard. But when you get to weird stuff like this, it's almost easier if you can think your way through it, like what makes sense. If I'm trying to calculate a volume and I've got some circumference and I need to find the radius first, how do I put these formulas together? You can kind of think your way into an answer without maybe even realizing you're doing this composition of functions, but you're using formulas and combining them together. When you're dealing with kind of abstract random formulas, it can seem weird, but if you can relate it back to a process that you can think your way through, say, okay, well, I'm going to imagine this is that other situation. I'm going to imagine this is the perimeter that I got. I'm going to plug it in here, and whatever story you want to imagine it's like, you can remember what the process is from having done this in a situation with more meaning. And the reason I did want to show you, like we talked about with meaning, doing these function compositions, but just mathematically speaking, sometimes you run across a formula, you don't really know what it's for, how it works, but you should be able to do the same process whether or not you yet have a meaning or understand how to use the formula that you see first. And sometimes by doing something else to it, then it becomes familiar after the fact. Now, these are just random things I made up. But let's look at the second example here. Finding f of g of x and g of f of x. What about for f of g of x here? Let me just copy f of g of x. Anyone have a thought of what f of g of x for number 2 is going to have in it? I saw it. Yes. Yeah?
Would it be 3 and then parentheses 1 over x?
So we're going to have, right, so we've got an x right here in f's formula that we want to replace with g of x, which is this 1 over x. So, yeah, g of x takes the reciprocal of something, and so f of x, I want to do f to the reciprocal of something. So you can think of it as f of 1 over x, but yeah, we're going to have 3 times to start this off. I'm just going to write it this way because it's easier. Ooh, no, it looks like a mess. I'll copy and paste. But yeah, this 1 over x would get squared, and apparently it doesn't like me copy and pasting little fractions. I'm going to have to do this the hard way. All right, let's see. I know I'm going to need something squared, and my something is a fraction. Oops. 1 over x squared. And I didn't put the parentheses in. This is like a bad equation editor. So apologies for the, I'll just leave it like that. You know what I mean? 3 times 1 over x squared. It's not cooperating on that one today. And what's the rest of this? Minus 5 times,
5 over x.
yeah, 5 over x or 5 times 1 over x, however you want to write it. Yeah, I'm just going to 5 over x. Instead of 5x, I'm going to have 5 times 1 over x. And 5 times 1 over x is 5 over x. Apologies for the poor equation editor. I don't have yet the normal equation editor installed on my new computer because I forgot about it. I haven't been typing up math in a while. But, again, this one's f with function g's result. Function g's result is 1 over x substituted in for the input variable. So 3 times 1 over x squared minus 5 times 1 over x, or 5 over x. So if we want to do this the other way around, g of f of x. Thoughts on that one? What would that one look like? Yeah?
1 over 3x squared minus 5x.
Right. So g of x takes the reciprocal of x. G of f of x is the reciprocal of f of x. So if I have g of f of x, it should be 1 over f of x. Ooh, that one turned it nice. Okay. So if I want 1 over something else, in this case, f of x, we've got 3x squared. There we go. 3x squared, was it minus 5x? Yeah, as you said. So, and I doubt this one's gonna, oh, it does. All right, so yeah, g takes the reciprocal, g's input, the output is the reciprocal of whatever its input is. 1 over x and x are reciprocals, unless x is 0, in which case g of x doesn't have a value. But g of x takes the reciprocal, so if I say g of f of x, it gives me the reciprocal of f of x, 1 over f of x's formula. All right, so that's the algebra end of generic function composition. Take a look at tabular. Now, I don't need to come up with a formula for these. These are just, I just typed in some random numbers here. Well, not too random. I picked some integers. But if I want f of g of 4, thinking about what that means, this is a sequence of two processes. First, like order of operations, start inside the parentheses and work your way out. So 4, find g of that, and then find f of whatever you just found. So starting with 4 as an input value, I want to find g of that. So g of 4, according to this table, is 2. Right? And so then 2 is what I'm going to use as my input to f, right? Because g of 4 is 2 according to the table. So what's f of 2 according to the table? 6. Because when the input to, as x, the input to a function is 2, the output is 6 for function f. So what about for question 2 here, g of f of 4? Anyone have a suggestion on this one? Yeah?
Would be 7.
Yeah, let's see. So how did you get that?
So first we got like 4, which was 1.
Mm-hmm.
Oh, okay, it'd be 3.
Right. Yeah, so we have f of 4. So input 4 to function f, and I get 1. And then inputting 1 to g of x, we get 3. So it doesn't matter that this is, it's like, well, that's not an x, that's a f of x. Well, but f of 4 is 1. As an, if I'm looking for g of x, this is a table where it gives me g of x's. So thinking as x is whatever I'm inputting. So if this is the input to function g, this is the output. If this is the input to function f, this is the output. This first line. But yeah, so g of 1 is 3. So, oops, 1, which is 3. All right, so what about f of g of 5? That's a little bit weird, right? So what's the problem here? What is g of 5? Right, and f of negative 5 is not something I know anything about. So this, if possible, well, I can't use the values in this table to find that answer because f of negative 5 is not something that I know. So that one has no answer according to the table. We don't have enough information to answer question 3. What about 4? G of 1. That looked kind of weird. But even though it's weird, we can do the same thing. What's g of 1, the inner part? G of 1 is 3. All right, so that means these two expressions are similar. The inner g of 1 is the same as the number 3. So g of 3? 9, right. So we can find these values using a table. Again, if these were, stories about like converting something from kilometers into inches and then into, I have no idea, yards or something. We could have bizarre formulas and just like look up stuff in a table. And those sorts of, like lots of times, okay, pre-calculator, back when my parents were in college in the 60s, yeah, they didn't have calculators to take with them to math classes, but they did engineering stuff still because they had their handy dandy, you could take it to class, book of values to look up. So you could flip through it and find trig values, you could flip through it and find squares of really weird numbers. So you didn't have to have a slide rule all the time, you can just like pull out, yeah. There's lots of stuff that you just like used to look up in tables because it was a lot easier than dealing with recalculating it all the time. So luckily, we don't have to look up everything in tables, but when you have tabular values, you can certainly use them to answer your questions even without knowing how to compute the function's values yourself. All right, now, just one last thing on composition of functions. I want to talk just a little bit about deconstructing functions. There's usually multiple ways to do this. But if you see a function that's more than just a single operation, more than just like f of x equals x plus 2, or f of x equals 3 times x, if it has more than a single arithmetic computation in it, more than a single operation, then you can think of it as two separate processes, just using order of operations, make this back into two functions, or more, somehow or another. And so each of these functions, h of x, has a couple of different processes, at least. And I think all of them have at least two different operations. I think they all have more than two operations in them. So that these could be split into multiple functions, but just thinking of kind of two chunks. Think about how you could construct, thinking about order of operations, two functions that could take the place of the single one. Now, this seems like a weird thing to do. It's like, well, it's nice to have it all condensed into one. Yes, it is. When you're in calculus, some of the things you're going to need to do is think about the separate components to a function, especially if they're different types of operations. Like adding and subtracting, those are kind of similar to one another. Taking a square root is a completely different sort of operation. And in calculus, one of the things you're going to be finding rates of change for non-linear, y equals mx plus b sorts of functions involves coming up with a formula for what that rate of change is, or like the steepness of the graph is at various points. It depends on where you are. But doing that analysis involves kind of pulling apart a function and seeing what its component pieces are. This first one, for instance, it's part linear function 5x minus 6. But then there's a square root. And if you think of it that way, say, oh, well, this is kind of like a function whose rule is 5x minus 6 got stuck in with another function whose rule is take the square root. So if I wanted to make a function f and a function g so that I do f of g of x and it comes out to this. So thinking about order of operations, if you were evaluating this manually, square root of 5x minus 6, you plug in the x, multiply by 5, subtract 6, and then take the square root. So the first piece of that is the linear equation part, which you could split into two parts, the multiply and the subtract. But let's say this is our first part. In terms of writing an expression f of g of x, that means I want this first part to be the 5x minus 6. And my f of x something about a square root. And I'm just using kind of calculator or iMath notation, SQRT, to save on this annoying equation editor. But if I want f of g of x to end up to be this, f of x should be the square root of what?
Square root of x.
Yeah, square root of x. So that if I do f of g of x, this 5x minus 6 gets plunked down in place of that x. So if I have these two, this would make h of x as seen if I do f of g of x. Now, if you wanted to, this minus 6, like there's kind of three processes here. There's a order of operations wise, multiply by 5, then subtract 6, then take a square root. So we could potentially split it into 3 parts, or I could have had the minus 6 as part of f. This would also work, right? So there's usually a lot of ways to deconstruct a function, but I just picked the way that, based on the fact that I've done a lot of calculus, it's kind of useful to separate out linear function, square root function. Or like one's kind of and do this to the whole thing. If I'm going to separate this into just 2 parts, might as well have 5x minus 6, easy enough to calculate for any value of x. Take the square root of what you just got. Seems like a nice end to that, instead of subtract 6 and take a square root. So think about how you could do the same thing with numbers 2 and 3. Separate these out into a function f and a function g, so that f of g of x comes out to be the expression on the left. So that number 2 says 1 over x minus 8 quantity squared. And number 3, 4 times x plus 2, where the x plus 2 part is raised to the 8th power. And certainly don't multiply that out. We're just trying to deconstruct this into a couple of pieces. All right, so let's take a look at these, and we'll move on to another topic. But 2 and 3, there's probably several different ways you could split these up into 2 pieces. But again, if I want it to be f of g of x that comes out to this, then maybe think of g of x as the first part of this order of operations wise, putting together a result that we want. So oftentimes, again, the easiest way, like if I were plugging in a number for x, what would I do with it first? Well, that's going to be part of what your function g is. And I just want to split this into two pieces. So anyone have an idea of something to use for the first piece of computing h of x? Yeah.
X minus 8.
Sure. All right, so g of x is x minus 8. So I'm going to plug in an x, I'm going to subtract 8 from it. So then I need my function f to do the rest of this computation, which means I have kind of two more things to do. Yeah.
1 over x squared.
Yep, 1 over x squared. That should do it, because, x squared. Here, I'll write it like that. So, again, if I did f of g of x, this whole x minus 8 would be in that spot. 1 over x minus 8 squared. Did anybody else split this up a different way? All right, just like the last one, I could have had this like minus 6 over here, or I could have had it under the, like with this x here in the square root symbol. If I wanted to, I could have had the squared take place over here, and then not over there, x minus 8 squared, and then do the reciprocal. Or, as we had the first time, just x minus 8, and then do the reciprocal square, because it's kind of three things that have to go on. X minus 8, square it, and do 1 over that, which is reciprocal, or 1 over x to it. It doesn't matter which way you're doing this. It's just like a practice pulling these apart into their component pieces and writing the functions, which is sometimes the trickiest part, when it's like, oh, and 1 over that. How do I do 1 over that? Oh, 1 over x. What about this last one? H of x equals 4 times x plus 2 to the 8th power. How about an idea for a first piece to this, the g of x? Yeah. X plus 2. Sounds good. So g of x takes x and adds 2 to it. And then I need f to do the rest of everything. So what does f have to do with that output?
4x to the 8th power.
Yep. Take that result, raise it to the 8th power, and multiply by 4. But again, the 8th power, just like in the last one, could have been on the first part, could have been on the second part, and either way, we'd end up with the same overall result. Because there's kind of three pieces to this one also. Add 2, 8th power, times 4. So in any case, this is called function decomposition, which is useful in analyzing functions, and you're going to find it extremely useful in calculus in dealing with how do I separate out this function into its pieces. So this is separating out something into a linear function and a power function, 8th power of x. Because if you remember learning about different power functions, maybe like a toolkit of functions at some point in time in an algebra 2 class, something like, all right, squared looks like this, cubed looks like that, 4th power looks like this, and well, if you can separate out things into specific types of functions, whether it's linear or otherwise, then you can analyze how they change and grow or shrink over time, or as you move across a graph. All right, so what I want to look at next is inverse functions. So, and if you didn't see this, there's a 3.6, I clicked on it earlier in class, 3.6 lesson that's going to be due on Sunday. I actually want to take a look at the beginning of that right now. And there's 3.6 homework due by the end of Tuesday next week. 3.6 is about inverse functions. And inverse functions, all they're functions that undo one another. Like inverse operations are things you use in algebra all the time. Like if you're dealing with an equation, there's a plus 5, you subtract 5 from both sides to help solve it, because addition and subtraction are opposite operations or inverse operations. Multiplication and division, same thing. Inverse functions, well, have to undo a whole sequence of processes sometimes. Sometimes they're as simple as just, oh, this one adds 5 and this one subtracts 5. That's what our function rule does, adds 5 or subtracts 5 from an unknown. then those two are inverse functions to one another. But if it's a whole sequence of processes, where it's not just a single operation, it's maybe easier just to think of them as inverse of an entire process. One undoes the process that the other does. So I'm just going to click on this here. And this is something that I want you to look at thoroughly over the weekend, but, and I knew I got this from someplace, this function f of x is a function f of x equals x plus 5. So the example that I was just kind of saying off the top of my head, whatever value for x we put in, this adds 5 to it. If I want to undo what function f has done, the opposite of adding 5 is then subtracting it back off. Or thinking algebra-wise, if there's a plus 5 and I subtract 5, I'm back to whatever else was there apart from the 5. So this expression, you can see this table, 0 for x corresponds with 5 for f of x, and so on. It's a simple function, just adds 5. So a function that undoes or reverses the process of f is said to be the inverse function of f, and the notation for that is a little exponent -1 on a function name. It does not mean like -1 power reciprocal, but that's where it comes from, because the reciprocal is the inverse operation to like a multiplication. So like multiplying by 3/4 and multiplying by the reciprocal 4/3. Those are inverse operations. We use that -1 exponent not to indicate that I'm taking a reciprocal, but just to mean the same thing as undoing function f. So the reverse of function f, or the inverse of function f, and sometimes if it's a single process, lots of times we'll say reverse. Reverse, inverse, just undoing something, would be subtracting 5. And I can call it f inverse, or I can call it something else entirely. But if function h is the reverse process, or undoes function f, then instead of adding 5 to input values, it would subtract 5. So 5 as an input, I subtract, and it goes down to 0, which is exactly the opposite of what function f does. Function f takes a 0 and turns it into a 5. Function h, or function f inverse, takes a 5 and turns it back into a 0. So the idea of this in terms of ordered pairs, input-output pairs, corresponding pairs of numbers, is that between a function and its inverse, those pairs are going to have the reverse rules in the function. So an input of 6.5 to function h has the same rule as an output 6.5 in function f. And in terms of meaning, now these didn't have any meaning to them, but let's say that x was the, wholesale price of something, and then function f, we marked up the price by $5 before we sold it. So whatever you got it for, you got some free stuff, you got some stuff for $1.50 at your business, you got some for $6, $10. You're gonna mark everything up by $5. Weird business practice, but whatever. Mark everything up by $5, there's the price that you're gonna sell them for. $5, $6.50, $11, $15. But then someone coming into your store knows that you do that. Like, oh, this is $5. You must have gotten that for free. $6.50? Oh, well, that probably cost you $1.50. Because I know you always mark things up by $5, so I can work backwards and figure out what you must have paid for them. So, again, weird business practice, but you can make a story to go along with these. Whatever one does, the other undoes. Or you can think of, if I know how this function works, I should be able to undo it, work backwards, and figure out what I had to have started from. But notice then that the input and the output variables are different. They have different quantities in those places. So in the case of the weird example I just made up, x here stands for these wholesale prices, and f of x would be the prices sold in the store. And then down below, the input here is the prices that we sell things for in the store, and the output is those wholesale prices or purchase prices. So the input and the output have opposite meanings. The quantities that are there are reversed in terms of their position in the function, whether that's what we start from or that's what we learn or compute. So in terms of inverse functions, I know one of the things that most people remember about dealing with inverse functions at some point in time in an algebra class is like something about like switch some variables and solve around. But if you switch the variables, that's kind of weird. Like if p stood for perimeter and you put the p where the side length was suddenly, like that's really bizarre. So it's, if you have generic x and y's that don't mean anything, sure, you can switch variables around if that makes you happy. But more important than anything to do with changing one variable and calling it a different letter all of a sudden is just we're undoing processes. So generally there's some algebra involved. We're going to solve for the opposite variable if I have a function to start with. Now if I don't have a function to start with and I just want to interpret things, then I don't have to worry about like solving. I'm just going to look at this and see what I need to do. So h of f of 0. Well, f of 0, according to this, was 5. H of f of 0 would be then h of 5, which is 0. And that should make sense because h and f are inverse functions to one another. One undoes what the other does. So even though it's not written as a formula like plus 5 and minus 5, that's what this is. I'm taking 0 and I'm adding 5 and then I'm subtracting 5. Or this is an algebra rule where I had an operation and then I use its inverse, which gets me back to whatever I started with, or it kind of gets that 5 out of the way. Like I was talking about, if you had an x plus 5 and then you subtract 5, you're back to x. So when we're dealing with a function and its inverse, it's like dealing with an algebra equation where you use opposite operations to strip away the excess. So h and f done in sequence to this input of 1.5. I have 1.5, I do function f, and then I do function h. Whatever f did to it, h is going to undo again, so guess what my result is? H of f of 1.5. If h and f are inverse functions, should just be 1.5. Because, and I can look at the tables and see that, h of f of 1.5. F of 1.5 is 6.5, 6.5. H of that, oh yeah, is 1.5. H does the reverse thing. So whenever I do this composition of a function and its inverse, I'm going to get back the input that I originally started with. So if I have some input variable, input value rather, apply one function to it, and then apply that function's inverse, it kind of gets rid of the fact that I used the first function in the first place. So h and f like cancel one another out. I'm back to this 1.5. And it doesn't matter in what order either, as long as the input values are defined, as long as all these values are defined, h of 15 means something. H of 15 is 10. F of 10 is 15. So, doesn't matter the order that I use. If these two functions are inverse processes, whether it's a single operation like add 5 or subtract 5, or if it's a sequence of events, if they're actually inverses to one another, whatever one does, the other one undoes. And so having them a composition like that of a function and its inverse will always result in back to whatever that variable is. In this case, there are numbers 0, 1.5, 10, etc. But even if it's just a symbol x, same thing. If I wanted to know what h of f of x is, I didn't even write out the formulas, but that'd just be x. It's that plus 5 minus 5. The 5s drop out. So here this is with the formulas written out. I'm going to skip over that. I want to look at something else that isn't just plus 5. All right, so there's no lead up to this. This is just a standalone question. A rocket's launched upward from a launching pad, and the function h determines the rocket's height above the launching pad, measured in miles, given that a number of minutes t since the rocket was launched have passed. So think about these two questions. The first one, there's like 4 statements here. I'm gonna zoom this in a little closer in case you can't see on your device. We have connectivity in a couple corners today. But a rocket's launched upward. What's the equality? H of 5 equals 552, tell us. And what does H inverse of 874 equals 8 tell us? And there's a sequence of statements. Let's see if I can get this. There we go. To be slightly bigger here. Read the sentences carefully. I don't have a formula for H, but I know what its input and its output mean. So therefore, I should also know what the input and the output to its inverse function mean, what sorts of things they are. So what about for question A? H of 5 equals 552. There are 4 statements there. Only one of them is correct. Which one is it? 1, 2, 3, or 4? 3. Okay. Statement 3. The rocket is 552 miles above the ground 5 minutes after the rocket was launched. So, meaning that 5, the input to function H, is something about minutes, and the 552, the output from function H, is something about miles. So the rest of these, the first option says the rocket travels 552 miles every 5 minutes. That's got the right units. 552 is miles and 5 is minutes, but that's describing a rate of change. So it's saying something about the rocket going at a constant speed, and that's not what we know. All we know is by 5 minutes it was 552 miles, or it traveled 552 miles, and that's all we know. We don't know if it's at a constant speed or not. So option A would be assuming a little too much about this, but it has the right units. The other ones have the wrong units. I guess B has the right number of miles, but currently doesn't have anything to do with H of 5. What about question B? What does the equality statement H inverse of 874 equals 8 tell us about the rocket? Again, of those 4 statements, only one of them is true. Is that 1, 2, 3, or 4? Yeah, the 4th one. If the rocket is 874 miles above the ground, 8 minutes have elapsed since it was launched. Again, so H and H inverse have the reverse input-output meanings from one another. So the input here, this 874 that's in parentheses, would be something about miles, and the output would be something about minutes. So 874 miles and 8 minutes is what we're relating here, and with the details of the question looked at more carefully, yeah, this should be 874 miles above the ground, 8 minutes have elapsed. It's not every 8 minutes or anything like that. We're not making extra assumptions, like travels 874 miles every 8 minutes. Maybe it does, maybe it doesn't. Probably not. They seem to not go at constant speeds, those rockets. But in terms of these 2 questions, they relate the same 2 quantities, but just in different orders, how they're used in the notation, because one's with function H, which was defined in the first sentence, and the other uses H inverse, which then must mean the opposite order of relating those 2 quantities. All right, so you'll see in this there's some, you can play around with this, look at different modes of, if I can click on this, it doesn't want me to while I'm in presenting mode. But we can play an animation, look at different modes of this, watch candle grow and shrink. You'll get some practice writing formulas for these sorts of things, again, starts at a certain height and shrinks by a certain amount based on how many minutes have gone by. But we can write the inverse function to that, which would be okay, if I know what height it is, how many minutes have gone by. So the standard way that we did this before was based on minutes, determine the height. But obviously those two things are related. We should be able to find that the other way around too. Based on how high it is, how long has it been burning? And so the function in its inverse, calculate those two things about this burning candle here. And it's just a matter of these coordinate pairs, 3 minutes, 11 inches tall. Like which one is the input and which one is the output to the function we're concerned with. But they both relate the same two quantities together. Let's see, there's some more stories there. There's something else down at the bottom. This is using the graph. Where is this? Sorry. Candle. That's the one I was thinking of, I think. All right, here we go. I was just looking for, there's another standalone question. Joan traveled 3.9 miles from his house to the entrance of the freeway, and he turns his cruise control on to 72 miles per hour. So we want to find a function g that determines his distance from his house in terms of the number of hours since he entered the freeway and turned on the cruise control. So we should be able to, even though it's kind of a complex situation, use the amount of time that's passed to figure out how far he is from home, or use his distance from home to figure out how long he's been traveling on the freeway. So think about this for a little bit. It's a little bit tricky. Again, he traveled 3.9 miles from his house to the freeway and then turned on the cruise control to 72 miles an hour. So he traveled 3.9 miles and then started going at a constant rate after that. So think about, let me zoom this in again a little bit. Think about how I could write a function g to determine his distance from home t hours after he entered the freeway. And then there's answer a question. When he's 100 miles from home, how long has he been on the freeway? And then find this inverse function. If you can write the original function, you can do that inverse function maybe algebraically, or just think about what you did to answer question B. But take a couple minutes. Think about Joanne traveling here. And see what we can do with this. If you're trying to write a formula, a function rule, and are stuck, maybe think about how you'd compute this for a few different example numbers. Like, what about 1 minute after he's on the highway, 2 minutes after he's on the highway, 3 minutes after he's on the highway? Think about how you'd compute it for specific numbers and see if you can generalize that for t. Oh, I guess it's hours, not minutes. Sorry. Because we've got miles per hour. Much easier to use hours. Alright, so some review kind of built into this question here. Being able to write functions expressing constant rate of change, going at a constant speed of 72 miles an hour for t hours. If that was the end of the story, that's an easy formula, 72t, right? 72 miles an hour for as many hours as we need. What do I do with this 3.9? Yeah, just add it, right? So at time 0, meaning 0 hours on the highway, not 0 hours since he left home. At 0 hours on the highway, we know he's traveled 3.9 miles already. So all of his results are going to be 3.9 or bigger. But when he gets on the highway, he's already starting at having traveled 3.9 miles. And then he goes 72 miles an hour for every hour past that. So like past when he got on the highway. Goes 72 miles an hour added for every hour he's on the highway. Or 72 miles added for every hour he's on the highway because he's driving 72 miles an hour. Or whatever speed it is that you have him in your question. So g of t takes the number of hours on the highway and tells you how far he is from home, even though not all of this was on the highway. The other part of it was a number of miles that we just get to tack on, 3.9 extra miles beyond what he drove on the highway. So if he's 100 miles from home, and we want to figure out how long he's been driving on the freeway, what is it that we could do with this formula? Plug 100 in for g of t. Yeah, so this formula result, 3.9 plus 72t, has a value of 100. Because this takes a time as an input and gives me miles as output, miles that he's driven altogether. Right, so if we have 100 miles driven altogether, then the result of using this for some value t is 100. And I don't know what it is, but as a reminder, if you don't want to compute it out manually, this is a calculator line. So enter a mathematical expression. It's like, well, let's see, if I set this equal to 100, to solve I'd have to subtract 3.9 and divide by 72. So 100 minus 3.9, and then divide by 72. You don't have to grab a calculator and calculate this out separately. You can just write the expression like that. And you can see it's computing it. It's about 1.33 hours or 1/3 hours on the freeway, approximately. If you rounded this to like 5 or 6 places, it'd probably be marked as correct, but you can just type it in as an expression and not worry about having to round. All right, so the other reason I wrote the expression in like that, if I want to find g inverse of d, so d is the distance he is from home. So if I want to be able to plug in distance and get, well, the other part of original function, the other half of the relationship was time he's been driving on the freeway. G inverse of d means I want to be able to plug in a distance and get a time. Well, just did that up here with a specific distance, 100 miles, but it could be any distance, right? So just like that computation, only with a d. D minus 3.9, take any distance, subtract 3.9, and then divide by 72. And that's the function. It wrote the g inverse of d equals for us, so I didn't have to write that part this time. But this would take any distance and tell us how long he's been driving then. So it's the same process that you'd use for a single number, you can do for any number because it's the same formula every time. And that's how algebra works. Regardless of what the symbol is, you solve for it the same way. So what about this last part, g inverse of g of t? What is it? Yeah, just t. I don't have to do any fancy solving. Now, if you really want to substitute g of t's formula into G inverse in place of this D, you can do the algebraic simplification, but you can see, oh, this G function rule, 3.9 plus 72t. If I put that in here, the first thing I do is subtract 3.9. Okay, so it'd be down to 72t. And then divide by 72. Oh, so that would be back to t. Those are opposite, it's a two-step solving that we had to do, subtract and divide. And so those two steps in sequence, in the right sequence, undo one another. And so we're back to what we started with, or t in this case, in general. For any value, this g, applying function g and then its inverse, would get you back to whatever value you started with, including a general value t as a variable or an unknown representing whatever amount of time we want. All right, so we did a bunch of questions from this lesson, but that is one of your assignments to look at for over the weekend. Let's see, so I'm going to get back out of this. Oh, I know what I want to show you, the test review. So the test review, as I said, you can get to it from the announcements in Canvas. It's in this upcoming things to do, the most recent announcement that I posted on Tuesday. Has a link to that exam review there. I was trying to put it in iMath and it was not liking linking functions, so I didn't put it in there yet. I'll try again after class today. But as I said, it's really long. We're not going to go through all of this in class. I'm going to give you a list. I'm going to give you a document that's answer sheet also. I do want to talk about just a little bit on this front page because it's kind of not in any particular order, and some of the stuff on this front page is stuff we were just talking about. But as it's really long, it's numbered up through 50, but like 48 is 3 questions, and 47 is 3 questions, and lots of them are like that, so it's like 150 questions in one. Your test is like 25 questions, just 25 questions, and that's it. So much shorter than this. This has a whole variety of questions, some with graphs, some with formulas, some with just stories to work with and expressions and define this and that. Some of this should look familiar. I can see there's a box. You should see some of the same examples just to like remember thinking about those. But just on this front page, h of x is x cubed minus x plus 10, g of x is 2x plus 2, find h of g of x and h of g of 1. Huh, okay, that seems like stuff we just did. But then question 2, linear relationship between x and y. Here's a table of values with a blank in it. The first question is to fill in the blank. But then writing expressions that relate delta x and delta y, the changes. And then writing an equation that relates x and y, the actual values of x and y. So this goes back to like the second week of class, and then I tried to do a quick recap of that when I came back the third week, talking about proportionality and constant rates of change. It says right here it's a linear relationship. Linear relationships indicate we've got a constant rate of change or between two functions, or that their changes are always proportional. We talked about is it like boxes of candy and the prices of those, and it's $2 per pound something. Changes are proportional in linear relationships. The x and y values may or may not be. It depends on the specifics. Like, do we have that 3.9 extra miles off the highway that Joanne drove or not? Do we have any extras? Who knows? You'll have to do some investigations here. But you'll see the main topics here. We've got constant rates of change for Paolo running on the beach, and here's not a table of values, but just a bunch of different details. We've got formulas that we can use to find either the declared output value, like the volume in this case, or you can find the radius. Or actually what this one's asking you to do is a composition of functions. Because it's like, well, what if I know that the radius is changing? It's a snowball and the radius is melting. Well, the snowball is melting, so the radius is shrinking. In fact, it's decreasing at a rate of 0.4 centimeters per minute. That would be a constant rate of change. So I could write a formula for my radius, and pop it in that spot there. And then I have a formula for volume based on how much time has gone by, how long this snowball's been melting. So lots of kind of combinations of things we've talked about, but the main topics, and we've got one last little part that I just didn't want to bring up today, that's just a different use of composition of functions, kind of, and constant rate of change ideas. We'll talk about that on Monday because it kind of combines everything together. But we've got, from the beginning, just the ideas of variables and their meaning, and functions and inputs and outputs, but compositions of functions and constant rate of change functions and inverse functions. We're dealing a lot with functions and their structure, how to write relationships and understand what we're talking about. So look through the review sheet for sure. I do have, like I said, stuff posted for you to do. Let's see, let me just get back to the main page of this. The 3.6 lesson that we were just working on, I have that due, like finish up the practice. I mean, if you didn't have it open, start it and then finish it by Sunday night. And then there's also homework, similar sorts of questions, but we didn't just go through half of them. That's due by Tuesday night, so I'll see you again before that. Keep in mind that we've got the tutoring center online that's open Monday through Friday, variety of hours. They just switched a little bit because someone changed their hours, but those are posted right below this calendar here. So there's an assortment of times, some in the evenings on Mondays and Wednesdays, mostly mornings on Tuesday, Thursday, Friday. But any of those hours, that's people like me and IAs and grad students, a whole bunch of people that work with the course and some other math tutors are available at the Zoom location where the the instructions are here. Just open your Zoom, and then you want to join a meeting, a specific meeting, and the name of the meeting is saved in the ASU system as Pathways Tutoring. So you can just type that all one word, and it knows where you want to go. So, in any case, that's the online tutoring for this. There is a math tutoring center in general that's, I don't even know which way I'm facing. It's that way. It's in the Wexler building, but this has tutors that are specified just for our specific course. And so when you go there during the time it's open, you're guaranteed there's going to be people that know what you're talking about. They've seen your homework before, probably even. They know what you're working on. They're aware of when your test dates are. It's not just general tutors. It's people that know about our course and have worked with it and or are working with it, teaching it right now. So study well. That's it for today. And I will see you on Tuesday.